Greetings and salutations. Welcome back to another episode of Not So Sirius. Today, we'll be talking about the solar system. Underneath its seeming banality, our solar system is critically different from the rest of the universe in that we live in it. Unlike the rest of the universe, which we could not hope to explore in the foreseeable future, the solar system has been open to physical exploration for the last 70 years and observational exploration for millennia. It has been and continues to be an important testbed for scientific theories and has been used to confirm some of history's greatest theories.
But before we get into today's episode, it's time to cover some interesting scientific news. Hello, my name is Talon Gilchrist, the Everything Astronomy News Reporter. For today, we have an article by ESO in which they state that the Very Large Telescope has discovered evidence that 6 galaxies are orbiting around a supermassive black hole in the early universe. This came about when they noticed a cluster of galaxies surrounding the black hole along the cosmic spider web of gas. Some may ask what this so-called spider web may be, but Marco Magnoli, an astronomer at the National Institute of Astrophysics, may have the answer. Quote, "The cosmic web filaments are like spider's web threads," end quote, explains Magnoli. The galaxies stand and grow where the filaments cross, and streams of gas available to fuel both the galaxies and the supermassive black hole can flow along the filaments. Most astronomers believe dark matter to be the key to these cosmic webs, and hope to use this theory to describe the early evolution of galaxies and supermassive black holes. Thank you for tuning into this week's episode of Everything Astronomy News. This is Talon Gilchrist signing off.
So, the solar system seems simple in that we all learn about it at a very young age in middle school and probably even elementary school, and then most people just stop thinking about it. And so this basic structure of a central sun being orbited by 8 planets sticks with most people for their entire lives. But beneath this deceptively simple appearance, there's actually a lot of complicated stuff going on and some really interesting stuff. For example, outside of Neptune, there's this thing called the Kuiper Belt. And the Kuiper Belt is donut-shaped, and the donut is in the same plane as the other planets orbiting the sun. So all of the planets orbit the sun roughly on the same plane, and the Kuiper Belt lies on the same plane, but because it's a belt and it's a bit thicker, it's a donut shape. And inside this donut, there is lots of gas, lots of dust especially, and lots of ice. And the key feature of the Kuiper Belt is that it is donut shaped. Well, that is a key feature of it. Except it has been noticed that within this donut, there are some objects that are not moving in the same plane as the other objects orbiting the sun. And so that, for example, tells us that there is something inside the Kuiper Belt upsetting these objects. And this is why some scientists, and some pretty eminent scientists, are suggesting that there's probably a 9th undiscovered planet orbiting the sun that lives inside the Kuiper Belt. Were this planet to exist, that would be a truly huge ramification in the scientific field, because not only does it tell us that there could be 100-year lapse between us discovering the last planet and us discovering this new one. It's also a confirmation in some sense that the scientific method works, because by questioning things that we thought might be established science, we're actually discovering new things. But more about this Planet 9.
Yeah, so, the main idea with the Kuiper Belt and Planet 9 is even with the discovery of a Planet 9, it can also tell us a lot about the development of solar systems and the development of star systems. If you think about, we might have mentioned in a previous episode about star evolution. You have a star and a proto disk full of dust, but essentially this Kuiper Belt can represent that proto disk worth of dust. It's just a lot of it's dust, gas, ice, and a development of a planet nine that may be happening right now and is not necessarily full size. It can tell us a lot about how planets might form in the early days of a star system, where that entire belt worth of material is eventually being gravitationally pulled to one another, and then it's forming these planets that we might now just discover because they're newer and harder to detect.
Absolutely. And I mean, for example, just the very fact that all of the planets orbiting the sun lie in the same plane, even that is already somewhat astounding. And also, for example, something that most people probably don't think about is the fact that all of the planets orbit not only in the same plane, but in the same direction. Which tells us a lot about how the solar system evolved from nothing, or just dust, or the proto disk that Tommy was talking about, into the planets that we have. And so, in some sense, the solar system is really a great way to look at how things evolve in space.
It's a laboratory right in our backyard, and we can send. For the past 70 years or so, we've sent spacecraft and even humans to explore that backyard of ours, and we can apply what we learn there to other solar systems.
Yeah, absolutely. And for example, even with liquid water, for the longest time, scientists thought that life was completely unique to Earth, and that water was really only on Earth. And it's actually by looking at our solar system that we discover that water is really not unique to Earth in any way, shape, or form. We know that liquid water is a slightly different story, but at least for ice, for example, we know that there's ice on Mars because we've seen it. We know that there's ice on the moon because I think we haven't seen that. I don't know I actually don't know how we know that there's ice on the moon, but I know there's ice on the moon.
Right.
And there's ice in a whole bunch of places, which tells us stuff about how life might start. Maybe it tells us that water is really not that conducive to life, and that you actually need lots of other criteria to be filled before you have
the water just didn't spontaneously come to Earth. It came from the Kuiper Belt, which is home to short-term comets. Or comets are like asteroids, but they're are icy objects, and also they also came from the Oort cloud, which is even further out than the Kuiper Belt, and it contains long-term comets and orbit the sun. And so water is very prevalent, we think, the further we move out from the solar system, from all of those icy objects.
And many people this very summer saw a comet
Neowise
in their backyards and in the sky, and that looked really cool. That was the first comet I saw personally. That was very exciting. And comets are just they're just snowballs that come from probably the Kuiper Belt and get thrown into the solar system and pass by the sun. And as they get closer to the sun, the ice starts to melt, and it forms those really cool tails. But an interesting fact about the tails that I learned actually pretty recently is that there's not one tail, but there's actually two tails. There's a dust tail and a gas/ion tail. And so the dust tail is just trails the movement of the comet. So the comet moves in a direction, and the dust trail is directly behind it. But the ion trail, which is full of ionized gas, is actually is always pointing away from the sun, which I thought was an interesting thing.
And it's pointing away from the sun because of the solar wind, which are these high energy particles ejected from the solar surface that are blowing against the coma of the comet and blowing all the material backwards. And I'm not sure which one's more prevalent, the dust tail or do you know, Joe, or the ion?
I'm not entirely sure. I believe actually it's the gas trail, because at least in high school physics, and I think in maybe even intro to college physics, you learn that a comet's tail is always pointing away from the sun. So I assume that they're talking about, given that they tell you that the tail is always pointing away from the sun, and that the gas/ion tail is always pointing away from the sun, I assume that's the more prevalent one, or the bigger one. But even going back to the solar wind idea, it's been theorized that the Kuiper Belt is actually kind of dissipating and becoming less and less dense because solar wind is blowing through it and pushing things inside the Kuiper Belt away, which is kind of cool to think that the sun is blowing wind throughout our solar system.
I also think it's worth mentioning that with comets specifically from the Kuiper Belt, like the way they get to near Earth orbit where we can see them is actually pretty cool. I was doing some reading on this where I think I read that there's a region in the Kuiper Belt that's really close to Neptune within its gravitational field. And so what happens is Neptune kind of morphs this portion of the Kuiper Belt where it pulls these objects in. And then I think somewhere along the lines, these objects, they drift too far in, and then they get caught up in between Jupiter's and Neptune's, I believe, gravitational fields. And in that, they kind of get ripped apart. And so that's why you see a lot of dust inside the Kuiper Belt, as well as these comets, they just come into the gravitational field of Jupiter and they get pushed in.
Yeah, because
fly by, which is I think really
Neptune
cool,
is right at the border of the Kuiper Belt.
Far out,
right?
Jupiter or in Neptune,
and
all
I
the
mean,
way to like
Pluto spends a large part of its orbit
within
inside the Kuiper Belt.
Mm-hmm.
And I mean, and an interesting fact about Pluto, which is actually one of the reasons why it was declassified from just a regular planet to a dwarf planet, was because Pluto's orbit is not circular. So all the 8 real planets that we know of that are established has very circular orbits, but Pluto's orbit is actually very not circular. It's pretty oval. And also it doesn't lie in the same plane as all of the other planets do. So it's actually, I think Pluto is orbiting at like a 20-degree angle compared to the other planets.
But I think that, I don't know if Pluto is declassified because of the super elliptical orbit. I think it was the International Astronomical Union.
IAS. IAU.
The IAU. They came up with 3 distinct categories to define a planet, and there being 1, that a planet must orbit the sun. Number 2 is that it must have enough mass for its self-gravity to overcome the body forces, so that it's basically circular in shape, or just approximately circular in shape. And also, and 3, I think, is the reason why Pluto is declassified, but it has to clear its own path. And so with Pluto being amongst tons of other dwarf planets, similar in size but not as large, and it being in the Kuiper Belt with all these other objects, I think it just didn't clear its own path, and that's why.
I mean, Pluto spends, I think, about a third of its time being actually closer to the sun than Neptune is, because Neptune has a really circular orbit, and Pluto actually crosses that orbit.
Right.
And so it spends a part of its time outside Pluto's orbit, Neptune's orbit, but also a part of its time inside Pluto's orbit. And another thing, and I don't know if this is why it was declassified, but another unique thing about Pluto is that its center of gravity from its moon is outside Pluto's center. So to kind of explain what that means, or to kind of clarify what that means maybe, is, so for example, the moon orbits the Earth, we know. And so that means that the Earth is exerting a pull, it's exerting a gravitational force on the moon. However, the moon is also exerting a gravitational force on the Earth. And so that means that there's actually a point where there's a point that both the Earth and the moon orbit around. And that point is actually within Earth's surface. So if you drew to scale, or if you drew very carefully the moon going around the Earth, you would see that the Earth actually wobbles around this central point. But that central point is still contained within the Earth. And that's the case for the 7 other planets and their moons, but that's not the case for Pluto. Pluto has a pretty big moon called Charon.
Something like that.
And the center of the orbit between Pluto and Charon is actually outside of Pluto. And so that makes Pluto kind of unique. And the theory that I read about today, which is apparently still very much a theory and not far from being proven, is that Pluto might be an ejected moon of Neptune. Which would make sense, for example, because there's a lot of patterns that Pluto doesn't obey. So we have, for example, the fact that the inner planets in the solar system are rocky and the outer planets are gaseous. But then all of a sudden we have Pluto being rocky again. We have, the fact that all the planets are coplanar, but that Pluto is not. The fact that all the planets are elliptical. The fact that Pluto is not. That they clear their own orbits. The fact that Pluto doesn't. And so that has led some scientists to believe that Pluto could just be an ejected moon of Neptune. Apparently, a big criticism of that theory is that if you kind of look at the trajectory of Pluto and the trajectory of Neptune and you roll back the clock, it's very hard to, well, there is no time that Pluto and Neptune would have been in such togetherness. However, it's possible that, Pluto was knocked out of orbit or something. It's possible that something similar happened, which would then lend credence to that theory.
You could even, maybe, I didn't see this anywhere, but since it has a second large moon that orbits it, and it has 4 additional moons, one being named Styx after the rock band.
Wait, after the rock band and not the river?
No, Styx. It's named after.
But there's also a river in Greek mythology.
Yeah, no, it's named after the rock band.
Oh, interesting.
But you could even, maybe it was even broken up, and that could explain. It was previously orbiting around Neptune and was broken up.
Right. But talking about, ejected objects, and kind of going back to what Sam said with, comets in the Kuiper Belt, looking past Pluto, there's been these theories of the planet 9, which you might have mentioned already,
which we have mentioned already.
Yeah, but no, you have this object that's ejecting things out of the Kuiper Belt, and Neptune's also causing these issues. But having this planet where it's ejecting objects out of the Kuiper Belt at different orbits, maybe that could also be a cause of these comets, and maybe why some of these dwarf planets are having irregular objects. Maybe planet 9 is the biggest out of all of these planets, and maybe Pluto and all the other dwarf planets are different subsects that have to have interacted gravitationally with planet 9.
I mean, with planet 9, the theory of planet 9 that was designed to explain the odd orbital patterns of some object inside the Kuiper Belt suggests that planet 9 would be about 10 solar masses, which is apparently
not solar masses. Earth masses.
10 Jupiters.
10 Earth masses. Sorry.
Oh, Earth masses.
10 Earth masses. Solar. That would just be ridiculous.
I'd be like, geez.
But the apparently that is, from what I read, the most common mass for planets is between 5 and 10 Earth masses. So throughout the universe, that's the most common weight of planets. So
I think they also expect it to be a gas planet, not a rocky planet.
But and so again, that would this planet 9 might. It's the only problem with it is that it seems all very speculative at the moment. It just seems introduced to explain some things. But I mean, complex numbers were introduced in the same way. Now they're pretty ubiquitous. So Who knows?
And the biggest question.
Oh, sorry. Go ahead.
The biggest question asked about Planet 9 is, well, if it exists, why haven't we discovered yet? And why are they unsure about the models and showing that this could explain the orbits of other objects in the Kuiper Belt? And the reason is because it's extremely difficult to observe something that faint. It's in the Kuiper, or it's actually the Planet 9 in what's called the scattered disk, which is it overlaps with the Kuiper Belt. So the Kuiper Belt is around 30 astronomical units, or AUs, to 50 AUs, which is 1 AU is 93 million miles. But the scattered
disk, also the distance from the Earth to the Sun.
Yeah, the scattered disk extends up to 200 AUs, I think. And the scattered disk is what's really inclined, almost perpendicular to where all the planets orbit. And so that's what Joe was referencing earlier when he was talking about the objects that are super inclined compared to the orbit of our 8 planets. And what were we talking about?
The scattered disk.
I had a point to make.
Oh. Well, no matter, we'll come back to it. A really cool thing in the solar system is that the solar system allowed us to prove that general relativity was real. So, and that has nothing to do with with what Michael just said, just to be clear. It's completely different, but super cool. So when Einstein came up with his theory of general relativity, he basically predicted that that mass bends space-time. Wait, did I say something wrong?
I remember what I was going to say. I remember what I was going to say. I was going to say that because it's so far out from our sun, it reflects so very little light that it's very hard to observe with telescopes and modern observation approaches. And so hopefully in the future, as we send out further, more advanced telescopes, and we scan more of the night sky and look for these little deviations or these little specks of light, which would indicate a possible planet, then perhaps we'll find it. But that's the reason we haven't found it. It's because it's extremely
Yeah, I mean the pictures of
Yeah,
Pluto
that fine
taken,
precision.
the pictures of Pluto taken before, what was it, New Horizon
New Horizons.
flew by Pluto were horribly faint. I
Extremely
remember,
pixelated.
Yeah.
yeah, they were horribly pixelated. I mean, they
Mhm.
couldn't have been more than like 50 pixels across.
Mhm.
And they were incredibly unclear, and they told us nothing. From looking at them, they told you nothing about what Pluto could look like.
Right.
Of course, now we've flown by it, so we know. But seeing things that are that far is really quite difficult,
And
especially given that these planets don't emit their own light. So
Right.
I mean, and they don't cross in front of other light sources necessarily, because, for example, when we observe exoplanets, one of the best ways that we have to look at exoplanets is either to look at stars and then see if anything crosses in front of that star,
Mhm.
or to look at how the stars move, and so that tells us that there's probably something orbiting around those stars. But detecting
Right.
the exoplanet itself is really incredibly difficult.
Mhm.
And the same goes for these really far objects, because they don't emit their own light, and so they don't really cross in front of light sources, which means that it's really difficult. It's really hard to spot. It's really hard to spot a dark object in the dark. Kind of
Right.
like it's just impossible to find your phone at night or find your glasses when there's no light on.
Right. And the development of telescopes and, objects crossing one another, it also relates to what Joe was about to mention about the confirmation of general relativity, wherein we were able to develop telescopes that were able to see the precession of Mercury in front of the sun.
So maybe to explain, apparently what I've been told is that scientists in the late 19th century thought that physics was basically complete. We had discovered Maxwell's laws. Nearly everything could be explained. There were very, very few things that couldn't be explained, and people thought that was just a matter of time, and that the existing frameworks were complete. So, except that apparently there were still, as Lord Kelvin put it, there were still three big kind of like unknowns that people thought would just get solved soon, but weren't quite solved. One of those was black body radiation. No one could explain exactly why black body radiation behaved as it does. But an equally important thing was the fact that Mercury's orbit precesses. So what that means is that Mercury orbits in a roughly circular way, but that the circle moves a little bit all the time. And people just thought that was going to be explained in some other way, in the same way that we'd been able to explain the movement of every other planet.
And so, for example, given that previously, to explain these weird anomalies that they found with other objects, they just threw in a planet into the equation. They did the same with Mercury. And so in the late 19th century, there was a French astronomer who introduced the planet called Vulcan, what would later become Vulcan in Star Trek. But that was scrapped away when, as Joel described, general relativity was introduced.
And so people thought that, scientists just attributed this seeming precession of Mercury's orbit to experimental error at first. But then as, telescopes got better and better, and the measurements got better and better, and the calculations and the error estimation got pretty good, we started to realize that the precession of Mercury's orbit could really not be explained by the science of the time, or by, the mechanics of the time, if you will. And so in comes Einstein, who says, actually, cool thing, guys, matter curves space-time. And essentially, a prediction of that theory is that the sun bends space-time around it, and so that leads you quite naturally to Mercury's orbit precesses. And so that was a great explanation of that. And so Mercury's orbit was perhaps one of the reasons why we came up with general relativity. But then, come time to prove to one of the, I think the biggest test of general relativity was showing that that mass bends light. And so to do that, we use the sun. And I think this was in the 1920s. This was a very, very big experiment.
It's like 1917, 1918.
Yeah. And so during an eclipse, we know that the sun gets obscured, and so it becomes dark. And what Einstein predicts is that because the sun bends space-time, you might actually be able to see things that are behind the sun, because the light, instead of being absorbed by the sun, might actually bend around it. And but normally it's really hard to see things that are behind the sun because the sun is so bright. However, come eclipse time in 1917 or 1918, because the sun just becomes dark all of a sudden, you now have a platform to observe the stars perhaps that are behind it. And that is what they saw. During the eclipse, they were able to see stars that they knew were actually behind the sun, but you were able to see them because the sun bent light. And so our own solar system and our sun were instrumental in proving Einstein right and proving that his theory of general relativity was in fact a correct explanation of what was going on. Another cool thing about the solar system is that, for example, it teaches us about how things come about. As Tommy said, how we moved from just dust and a proto disk to more sophisticated, to more nicer planets and a more orderly system. And one of the cool things with the solar system is that our star is right by. And unlike every other star, which is really far, our own sun appears really, really big. And so, for example, we've been able to study the sun in great detail. And because of that, we've been able to learn about how other stars work as well. And chief amongst those is discovering exactly what radioactive processes are going inside the sun and what keeps our sun going. And so, it was by observing our sun very closely that we discovered exactly what nuclear processes were happening. So, the triple alpha process and the helium fusion and all of those.
The proton chain, the CNO cycle.
Yeah, all of those things.
But, looking at our own solar system, we have all these solved variables, but it also raises a lot of questions as, we're pretty close to the sun. So we seem, we're pretty confident that we know everything, within, Jupiter's orbit. But looking further out, like the Oort cloud, we don't necessarily know what's going on out there. It's very hard to see anything. We know it's, a cloud of gas and dust and ice, 10 to the power 4 astronomical units out, like 10,000 astronomical units out. There's still a lot of questions that we have to answer, considering even the Oort cloud is outside the sun's heliosphere.
And that's something we haven't even touched on, is the Oort cloud.
Yeah.
And it's so mysterious to us. There's trillions upon trillions it's estimated to be trillions and trillions of icy objects, similar to the Kuiper Belt, just way out there.
And even more strange, we've mentioned that all the planets in the Kuiper Belt are all on the same axis as everything else, but the Oort cloud is literally a spherical cloud that surrounds the entire solar system.
And that makes some sense. It makes sense that if the center of the solar system was denser than the outside, it would be a lot quicker to form planets and to stabilize its orbits and all of that. However, I just thought of this, but does that mean maybe that given enough time, that the Oort cloud will start to collapse and form more planets and become orderly like the center of the solar system?
That'd be interesting as we progress into studying other solar systems, is seeing our solar system in the future by observing solar system thousands of light years away in the Milky Way galaxy.
Yeah, because our solar system teaches us about the present, and so how solar systems might evolve, which then teaches us about how solar systems work far away. But it doesn't really tell it. But maybe if we then start studying solar systems far away, we can then take what we learn on them and apply them here, which would be
sort of seeing like historical snapshots.
Yeah,
our past or future solar system.
And the solar system is interesting as well because we can send probes out, and so that's how we finally have detailed pictures of Pluto, but also Uranus and Neptune, which are hard to take pictures of in general. And we've sent probes now. I think as of 2 years ago, we now have probes that are traveling outside the strict defined.
Yeah, I think the definition is. Like I know Voyager 1 crossed in late 2012, I believe. It crossed the heliopause, and the heliopause is defined where the solar pressure is equal to the interstellar medium on the other side.
Oh, so essentially that's saying that that's where the particle density inside the solar system becomes the same as it is just everywhere else in the world, in the universe.
Yep.
And I mean, now we have at least two spaceships or spacecrafts that are set for interstellar travel, which means that they're going fast enough such that they will never stop and never come back, and they will always keep traveling on their lonely course.
Except the one thing is, it doesn't really mean much for scientific progress because their main goals were to study planets in the outer solar system, and there isn't much they can do now. I do think they did send back data occasionally, and they did send some important information. Yeah, and they did send important information back once it crossed over the heliopause, so we could better understand exactly where this defining boundary is between our solar system and the interstellar medium on the outside.
And I mean, we have now imaged objects outside of Pluto, for example. So New Horizon crossed by an object that used to be called Ultima Thule, but has now been renamed. The name escapes me.
Is that the snowball one?
It's the snowman one. And it's basically, we'll put a picture up, but it looks like two snowballs that have been stuck together, and it's about 20 miles long. And that's interesting again, because it kind of tells us what might be floating around over in the Netherlands, in the far away, and which, it's always cool to know more. But it also tells us that it also might tell us, where did Pluto come from? Maybe it tells us that there's actually way more planets out there. Maybe it's telling us that planet formation is actually occurring out there. And I think it crossed by Ultima Thule in, 2 years ago? And it came really very close to it.
And not only are there thousands of undiscovered, if not millions of undiscovered objects in the outer solar system, but even nearby to Earth, there are things called near-Earth objects that are asteroids or comets that whiz by Earth all the time. And so, like this past week in the news, amateur astronomers caught on their telescopes a meteorite striking the top of Earth's surface and bouncing back up because it came in at a shallow angle. But that's not the case all the time. Many of the times, if large enough, those objects will pass through, as it did a few years back in some city in Russia, and actually, cause destruction on the surface of Earth. And so it is.
Yeah, that was in Siberia.
It is quite scary. Oh, that's the Tunguska incident in like 1910s. But there was one more recently.
I think that was also in Siberia.
Oh, also in Siberia.
I think we do have our atmosphere to protect us. So it's but all the time hit us. Like, we are protected to a certain extent.
But there's always there's every once in a while there are occasions where something comes within a reasonable distance of the Earth or the Moon, and astronomers or the telescopes that track these near-Earth objects are like, oh, by the way, there's this object coming by. It's not going to hit us, but it's coming fairly close.
Namely, the aforementioned comet Neowise, and also Muamua, which we can touch on in a second. But Neowise was a full comet, and we had no idea that it existed until a couple months before it was set to come by Earth. And there was actually, Neowise is a shocking property in the sense that we know now from looking at how it moves that Neowise has an orbital period of, I think it's 5,000 or 7,000 years. But what that means, though, is that Neowise has come by Earth before, and it came back. And the thing that I find completely mind-boggling is that 5,000 years ago, humans were around. The Egyptians were building their pyramids. There were tons of people doing their thing. And the night skies were really dark back then. So that means that people back then definitely saw comet Neowise come by. And it just somehow it got erased from the repository of human knowledge. Somehow humans knew that this thing existed, and nothing came of it.
Probably wasn't a way
it was
to
forgotten.
record it. Yeah, there probably wasn't a way to record it, or they probably didn't understand what it was.
Yeah, or maybe it was recorded and it got lost or something. But I find it truly amazing that humanity knew something and then just forgot it, and then we rediscovered it 5,000 years later.
And you mentioned 5,000 to 7,000 years from now, if we're still around as a human species on Earth, like when it comes back around, and they're thinking back to us, like, oh, why didn't someone record it? But we did.
Yeah.
Yeah, like if for some reason like the internet becomes obsolete, or like the cloud gets wiped for some reason, like no one's ever gonna remember.
Yeah.
Right.
I mean, it's definitely
that's how many generations away? Hundreds?
I mean, it's so many. Actually, not that many though, because if let's say that a human generation is every like 25 years, to make the math easy, that means that you have 4 generations every century, 40 generations a millennia. So really so you're only at 200 generations away. Which is not that much, in some sense. Like,
so I like you to name one person that you know from 200 generations away.
Well, I couldn't, because those people lived in pyramids, and I don't know those people.
Exactly, dude. The people in the future are going to think we're living in, like, pyramids, too.
Maybe. Although I don't think
for all you know, they could be, like, underground mole people.
Well, but...
Who's to say we know what's going to happen?
Yeah, to go back to Oumuamua, though, because that was cool. Oumuamua was this long rectangular object.
Cigar-shaped,
yeah. That parallelepiped-shaped.
Yeah,
I think that's the term. Yep.
And that like came into the solar system and then just left. And it's thought that was that is the first recorded interstellar traveler, if you will. So that means that this cigar-shaped object, which I don't actually know exactly how big it was, but it means that this cigar-shaped object came from not our solar system, visited for a brief period of time, and just left. And Oumuamua so the cigar shape was actually kind of tumbling into our solar system. So it was not just traveling in a cool, sleek way. It was kind of rolling around.
That's why it was also picked up by a lot of conspiracy people.
Yeah,
because of how it tumbled, then it seemed very not natural.
Right.
And I mean,
it's a cigar shape and begin with. Like, most people think like objects aren't very parallelepiped shaped, or whatever Joe called it earlier. But like, a cigar isn't normally what you expect from just a random rock,
Yeah, and I mean, apparently it did display signs of quote unquote non-gravitational acceleration, which is probably just saying that Oumuamua lost weight or something along the way, or it interacted with something, or something happened. Right. But some people's picked up on that and thought, that must mean that it's an alien spaceship, which I suppose the probabilities of that happening are non-zero, probably.
It was also the small shape, because I just pulled it up here on my other screen. It says it was about 3,000 feet by 40 or 400
and
feet.
we can pull up an image too, I think.
Yeah, for sure.
Well, I mean, but I mean, 3,000 feet is very, very long.
It's long, but
in the context of objects in space.
Yeah, space objects. Like, if you think about it, it's not longer than like, a couple dozen city blocks put together.
Yeah. So in conclusion, Oumuamua maybe an interstellar visitor from somewhere. Well, definitely an interstellar visitor, but maybe with people on board.
Yeah, but I think both of those examples, Oumuamua and Neowise, just show like, we're studying all these objects, and there's theorized objects, but then there's still things that we have no idea are coming. Every day on the news you can see, a meteor near past Earth, and you think, well, is this going to be it? Like, are we going to turn to the next dinosaur generation? But there's these objects that are just appearing all over the solar system that we had no idea existed, and then all of a sudden they're close enough where we accidentally pick them up.
And the unfortunate thing with these objects too is that we can only observe them and understand them for so long before they disappear out of sight. And so Oumuamua quickly passed into our solar system and is already out of our solar system and out of reach from our observatories.
I think it further shows that like there's so much more to learn from our own backyard, which is our solar system, right?
It's just crazy.
We don't know much, and we're looking into all these different areas of space that are so far away that we realistically can't ever get to. and yet there's all this evidence and all this information in front of us now that we can look into and hopefully use for those things that are further out that we can't really see.
And it's really interesting to take a more of a historical perspective at this and at our solar system, thinking back to, the Renaissance times when the solar system was being heavily studied by astronomers, including Galileo or Copernicus. And we thought we had a fundamental understanding of what our solar system was. Before Copernicus and Galileo, we thought that Earth was geocentric, the model where Earth is at the center of not only our solar system, but also our universe. And from there, we transitioned into the Copernicus model, where all of a sudden the sun is at the center. And then we start discovering all these little objects. We call them planets. And we say, okay, as it's the same structure we learned about, as Joe was mentioning earlier, when we're a young student in elementary school or middle school, where we have the sun at the center and the 8 planets or so orbiting it. But history has proven that it's extremely, extremely more complicated than that. And there's still so many discoveries yet to be made about our solar system.
I mean, namely, and I don't want to drag it on too long, but namely, the life on Venus thing, which recently came out. Scientists said, we found traces of phosphine in Venus's atmosphere. And
pretty cool.
There's
that's pretty
no
cool
explanation for phosphine in an abiotic context. Abiotic means there's no life. I learned that word.
Phosphine is definitely an organic compound that can only be made in non-natural ways.
In a general context, it just means that they found life perhaps on Venus,
or
outside Earth.
There has to be some kind of biological process that had to have made that phosphine, whether it was on Venus or somewhere else.
Although there are, I'm sure people listening to this have heard on all the other astronomy podcasts within the past, ever since the news broke out, that it was discovered phosphine in small amounts, though, about 20 parts per billion.
But it's still larger than some quantity than we can detect on Earth at some points.
But they did say that they did test it against other ways it could be formed that are non-biological, and so it is formed in the really high density depths of Jupiter. It's been found or detected. And what's really interesting is that Venus is basically a runaway greenhouse Earth, where it's the clouds are sulfuric acid or include sulfuric acid in its composition, and the surface is so hot that and so dry that life as we know it can't survive on its surface. But over the years of studying Venus, or the Venusian atmosphere, scientists have discovered that there's this layer, I think it's between around 20 kilometers above its surface and 60 kilometers, that there's this temperature range from around 0 degrees Fahrenheit to 200 degrees Fahrenheit, where if the temperature and conditions are correct, that some form of biological life could survive as we know it. And what's really interesting is that there's this layer, and that the phosphine wasn't discovered on the surface. It wasn't discovered at the upper atmosphere. It was discovered somewhere within this layer. And so that's really interesting, the implications. And I'm interested to see over the next year or so the follow-up observations and to see if there's an error in the original paper, and to kind of narrow in on what the possibilities could be for sure, phosphine being in the atmosphere.
So I think it's safe to say the solar system is cool. Don't think it's established science, and thank you for listening.
Hey everyone, thank you for listening to this podcast episode. This is Michael.
This is Sam.
This is Tommy.
And this is Joe.
If you're listening to this on YouTube, make sure to like, subscribe, and share with your friends. And if you're listening on Apple Podcasts or Spotify, make sure to leave a review. All of the show notes can be found either in the description below or on our website. Thank you again for listening, and we'll see you next week with more Everything Astronomy.